Okay, so I think recording has started. So good afternoon and welcome back to the session for Graph Neural Network. Uh, last thing that were about to finish in the previous session was the regular equivalence and the structural equivalence. Okay, so within 5 minutes, I'll quickly finish this, and then I'll move to the next module. So structural equivalence we have talked about. Equivalence means we are trying to find out the similarity between similarity of two nodes based on the shared neighborhood. Okay, so if there are more neighbors which are being shared, then the similarity value of those two nodes will be high. Okay, so that's purely based on the common neighbors. Okay, then the next set of equivalence was the regular equivalence, in which it is not necessary that we need to have some shared neighborhood. Okay, it may be possible that one node, we can say n1 is at the another part of the network or part of the graph, but suppose they have four neighbors and one neighbor is a triangle, then another neighbor is we can say something like this. One neighbor is a complete graph of 5 node, okay, and many other. And similarly, like this one is a triangle, one is a node of 5, and then one maybe okay, and so on. So in that case, although and they both belongs to the one graph, they may be distant to each other. Okay, but node 1 and node 2 and n1 and n2 are similar because their neighborhood are similar to each other, although not necessary that those n1 and n2 are directly connected, or not necessary that the neighborhood of n1 and n2 are also connected to each other. Okay, they are a part of network, so because of the 6 degree of separation, and this is a connected graph, so there will be some connectivity between the n1 n2 and the neighborhood of n1 n2, but there is no direct connectivity. Okay, so in regular equivalence, we do not look like neighborhood shared between the individual, but how neighborhood themselves are similar. Okay, so just by looking at neighborhood, so the neighborhood of n1 and neighborhood of n2 shares some similar property. So although they may not be directly connected, but in that case, n1 and n2 will have the same similarity value. Okay, so this type of equivalence, we call it as regular equivalence, which is important. And I think I've given you an example in the Netflix and the Amazon as well. In this, sometimes you might have seen that proper with some recommendation of to some product or some movies is being given to you, but with the message that a person like you have also watched this type of product. Okay, not this product, this type of product. A person like you of a similar interest had watched this type of movie, not this movie, this type of movie. Okay, so in that case, that recommendation system is not based on the connectivity. That recommendation system is based on the regular equivalence. Okay, so athletes are similar not because they, but since they know similar individuals, such as they have the coaches, they have the trainers, they have the other players, and so on. So based on their neighborhood, we can assign some similarity to those nodes, although they may not be directly connected. Okay, so Vi and Vj are similar, although not directly connected. So Vi is directly connected to Vks, they are the neighbors. Okay, and Vj connected to VLs. These are VLs are the neighbors of Vj. So Vi and Vj are similar when their neighbors Vk and Vl are also similar to each other. So first of all, the neighborhood are similar. If the neighborhood are similar, then we can say, okay, those two nodes are also similar. So this comes under the topic of regular equivalence. Okay, and it may be used for recommendation system as well. So that's all. I think just a mathematics part. Fine. So let's quickly move to the another topic. 6A, 5B, 5. Okay. Now, quickly, there are some more numerical values that let me cover it. Okay. So one was the structural and regular equivalence. Now we'll talk about spectral and spatial graph theory and then graph signal processing. So spectral graph theory, I'll read those statements, and those statements are self-explanatory. Wherever the explanation is required, I'll give you a proper explanation. So spectral graph theory studied the properties of a graph through analyzing the eigenvalues and eigenvalues of a Laplace matrix. Okay, so here, that's again, we are trying to come up with some numerical values based on their structural properties. So here, we will be trying to find out eigenvalues and eigenvectors, but with related to Laplace matrix. Now, what is a Laplace matrix? So Laplace matrix, that is a foundation. So Laplace matrix is often denoted by L, capital L. It captures the structural properties of a graph, particularly how the nodes are connected to each other. Okay, so that means it is somewhere an advanced version of the adjacency matrix. So unlike the adjacency matrix, Laplacian is more directly related to spectral graph theory and spectral algorithms. Okay, it will be a square matrix of order n cross n. Okay, similar to the adjacency matrix. Okay, or in an easy way, it is some modified version of adjacency matrix which stores one additional information about the graph. Okay, so it is a mix-up of. So that Laplace matrix is mix-up of two metrics. One is the adjacency matrix. Then definitely it will be a n cross n matrix. Okay, if the graph is very dense, most of those values are non-zero. If the graph is sparse, then most of those values are zeros in this case. Okay, fine. But it will be a square matrix. Then we have another matrix, which we call it as D, the degree matrix. Definitely it will be a diagonal matrix. Okay. Order of this matrix will also be n cross n, but there contains, sorry, I should not mention it as zero or something. I'll use some special symbols. So these were the degree of the node. So suppose this is a node 1. So degree of node 1 will be stored at this index. Degree of node 2 will be stored at this index. Degree of node 3 will be stored at this index, and so on. Okay. So this degree matrix will be a diagonal matrix. It stores only the degree of each node in the diagonal. Rest non-diagonal elements will be zero. So that's why I was hesitating to write it as a dot. D1, D2, D3, and so on. Okay, so only the diagonal matrix are non-zero, whereas non-diagonal matrix will be zero. Now, similarly, if I'm dealing with the adjacency matrix, but with a condition without self loop. Okay, so without self loop means this will be an order of matrix of order n cross n. I should not draw in this sense. It gives me a feeling. It might gives a feeling that there are product of two matrices. So it will be an adjacency matrix, but without self loop. So that means the diagonal element of this matrix will be 0. Okay, whereas non-diagonal elements are non-zero. Now I have two matrices, one matrix in which diagonals are all 0, non-diagonals are non-zero, and I have a different matrix which is D degree matrix, in which diagonal, whereas non-diagonal matrices are 0. So somehow if I merge both of them, okay, if I merge both of them, it might give me a matrix which contains both the information. Okay, so that L Laplace matrix is nothing. It is degree matrix minus adjacency matrix. Okay, when I subtract two matrices, okay, so this will contain both the information. This contains the degree, okay, degree of each node, and negative of all the adjacency matrix. So whatever the value was there in that adjacency matrix, negative of all those values will be there. Okay, and this order of this matrix will again be n cross n. Okay, and this matrix contains both the information, connectivity as well as degree information. So what are the what all are the properties? Row sums and column sums are all 0. Also called Kirchhoff matrix or information matrix. Laplace matrix of an undirected graph is symmetric and diagonally dominant. A smallest eigenvalue of L will always be 0. Okay, so that means, what does it mean? If the smallest is 0, that means all the rest of those eigenvalues are positive. Okay, so there will not be any negative eigenvalue, and the corresponding eigenvector will be a unit vector. Okay, spectral clustering is primarily developed for an undirected graph, and Laplacian matrix of an directed graph will be non-symmetric, but can be converted into symmetric. Okay, so I think that's clear. Any questions regarding this? I hope that's clear. That's simply basic mathematics.
Sir, I have a question.
Obvious and stupid question which come into my mind. Will I answer it? But before that, I would like to answer any query from your side.
Yeah, sir, can you hear? I have a question.
Yes,
yeah. So basically, the Laplacian matrix would be, a matrix which has got diagonal as the degree and rest everything as the minus of adjacency values. That's what it is, right?
it can be for weighted graph as well.
Okay.
Clear?
Yeah.
So the eigenvalues and eigenvectors of a Laplacian matrix explain the structural property, like how many connected components are there. Okay, so number of zeros will give us number of zeros in that eigenvalues will give me the number of component in the graph. What is the clustering structure, what the graph expansion properties are, and so on. Okay, so all these information can be extracted out from just from the Laplacian matrix. So where it can be used for the graph clustering and spectral clustering, so effective for detecting the natural clusters in a complex network. It's very well used for the graph partitioning. So crucial in parallel computing, image segmentation, and all. The third area is the dimensionality reduction, where it preserves the local neighborhood structures for a data point when I'm mapping them to a low dimensional space. And the fourth is the network analysis, where it helps to identify the central nodes, the community detection, what is the flow of the information, and so on. Okay. So how do we do that? So in spectral clustering method, we use the node adjacency matrix. Obviously, if I'm talking about node adjacency matrix, it is node to node, n cross n. Eigenvector techniques is used to determine the underlying correlating structures in the graph data. Fine. For an undirected graph, it contains n node of order n cross n, in which the entry aij corresponds to the weight of the graph between those two nodes. Okay, so it can be weighted graph as well. Okay, this essentially concerns similarity, how similar those two nodes are. Okay, if two indexes are similar, then that means those two edges or those two nodes, those two endpoints can be similar to each other. This entry is denoted by wij for the weighted graph, and all diagonal entries of a matrix W are assumed to be 0. Okay, so weighted matrix, diagonal entries for a weighted matrix. So this is the weights. Why the diagonal will be 0? Because self loops are not allowed. So no self loop means the diagonal entry will be 0. That's clear. Degree matrix is simply a diagonal matrix in which all entries are 0 except the diagonal values. Okay, fine. And the diagonal entries dii is equal to sum of the weights of all the incident edges. Fine. So Laplacian matrix L is defined by subtracting the weighted adjacency matrix from the degree matrix. So in words, if I say, it will be L equals to D minus W. Okay, so it will be a positive semi-definite. Okay, so that means positive semi-definite. This will be positive semi-definite means it means the eigenvalue can be 0, but cannot be negative, because all of them are at the smallest eigenvalue will be 0. So they can be multiple zeros. So we can, using those using those transformation, I can write it in the form of FLF transpose. Okay, so determine the appropriate. So in that case, if that FLF transpose, if I minimize, okay, so this minimize can also provide us with the good node partitioning. So if I can minimize this, so that will help me to partition my graph. Okay, fine. And there's that immediate observations are the indicator vector F111 is an eigenvector for corresponding to the eigenvalues of 0. Okay, same. There always exists an eigenvalue that is equals to 0. Fine. Must be an eigenvector since L is positive semi-definite. FLF can be 0 only for the eigenvectors with the 0 eigenvalues. Okay. This observation can be analyzed further in order to determine the number of connected components in a graph. So if there are more number of eigenvectors, eigenvalues, then the number of eigenvalue 0 will be equivalent to the number of connected components in a graph. Okay, since Laplace matrix diagonal has more weight, we can normalize it by d minus 1 by 2 a d trans d a minus 1 by 2. Normalized will be I minus a. Okay, so identity matrix minus adjacency matrix. So this will be the normalized factor. And this is the same theorem given a graph G, the number of 0 eigenvalues in a Laplacian matrix, the multiplicity of 0 eigenvalues equals to the number of connected components in a graph. So if somehow we have find out the Laplace matrix, okay, and Laplace matrix is nothing, just we can say subtraction of one matrix over the other, and from that we can find out the eigenvalues and how many zeros are there that will be equivalent to the number of eigenvectors. That's okay. So this is regarding the spectral clustering. Now, the one stupid question is why the Laplace matrix is considered as D minus W. Why can't it be W minus D? Okay. Why can't it be W plus D or D plus W? Okay, now, first of all, the first obvious answer is whoever have defined it, he might have thought in that way. The another way is, in this case, if my matrix would have been W minus D, okay, then the degree of each means this diagonal matrix will be negative. Okay, because degree of each node will at least be 0 or some non-zero value. So definitely when I do minus D, W minus D, when I subtract D from the weighted matrix, okay, so definitely all the diagonal matrix will either be 0 or negative. Now, degree cannot be negative. Okay, so that is the first reason, the degree of each node cannot be negative, because I know that my graph is at least, even if it is sparse, there'll be some zero matrix. Okay, but it will not have any negative degree. Okay, so there's no concept of negative degree. So that's why W minus D cannot be used. Okay, now someone would have come up, okay, why can't we add both the matrices? Okay, we can do that. Of okay, so that would have been, that would mix up both the detail. But in that case, if somehow we have we come up with some row column matrix, so row column manipulation, or any computation on those on those metrics, then in that case the degree property as well as the path, I mean the connectivity properties, will be added together. Okay, so that may have some other impact. Now in this matrix, when I'm subtracting it, okay, so means one effect can be negated over the another. Okay, so in that case, this might be just my intuition. Okay, it might be a reason, okay, just to take care, okay, the degree and weight, if one can be add one can be subtracted from the another, so that because mostly weights and the degree, they are correlated to each other. So it may not be, it might be possible that if I'm adding the same value, it might be superimposing, or it might become a very bigger value. Okay, so one value compensating the another one by just dragging it down. So it might be just my intuition, but I'm not sure whether that justification is correct or not. Okay, second one is graph signal processing. Okay, so signal processing means, if somehow if I can convert the graph into some form of sequence. Okay, so that I can use the CNN, convolution neural network, and all those techniques application. Okay, so this is a graph signal process. So in many real world graph, there are often features or attributes associated with those nodes. Okay, so that means every node will have some properties associated with this. So we call, they can be, we can say, they can be an example where nodes and edges have their own some set of properties. Okay, a combination of properties. So this kind of graph structure data can be treated as graph signals, which captures both the structural information in terms of connectivity between the node, okay, as well as the data, okay, which attributes at the node. So till now, till that point, whatever we have learned so far, we were focusing more on the structural information. Okay, or we can say we were focusing more on the connectivity part. Okay, the individual properties of a node was not looked at. So if I want to information also in a graph structure, so that I can process, or I can find out some new values, which is a mix up of connectivity as well as their own properties, okay, of the nodes. So graph signal processing consists of a graph, which is FV, and feature set of edge set of feature set of vertices, and some feature set with the edges, and a mapping function F defined from the graph domain, which maps the map node to the real values. Okay, so it will be a mapping function that can be represented from f vectors to some real numbers of the order n cross d, where n is the number of node and d is the dimension of the attributes of the nodes. So suppose, for example, a node contains 4 different attributes. I think this can be I think I'll be there's an example later in these slides, but as of now let me try to explain it in terms of chemical data. Okay, now, so that means in a chemical data, those nodes are the atoms or molecules. Okay, and edges are the bonding between them. Okay, and based on that, suppose for example, the basic structure that we have learned in the beginning itself, or we can say as we are very much familiar of, or we can say fed up of this shape, we call it as benzene ring. Okay, where these are the carbon atoms, okay, connected together by single or double bond, and in addition to it we have some other um, something like this. Okay, some other nodes, some other structures are also added to the graph and so on. Okay, now in that case, nodes are not, so this means, for example, this is a carbon atom, this may be some nitrogen, this is again not necessary, this is again a carbon, this is hydrogen, and this is an NH3 and NH4, whatever it be. Okay, so they all are carbon atoms connected to each other with some other nodes in some of the other form. Okay, so in that case, carbon may have certain different attributes. So the attributes are related to carbon, maybe its atomic number, valency, atomic weight, molecular weight, the ion, we can say the positive charge, negative charge, whatever it be, it can have multiple attributes. Okay, so these are the attributes which are associated, and suppose nitrogen may have a different things, oxygen may have different atomic numbers and their own set of properties. Okay, so with these, we can say, if I want to study or analyze this structure, it is purely based on the components which are connected together, the metals, non-metals, or whatever it be. Okay, and their individual properties and type of connections between them. Some may be single bonding, some may be hydrogen bond, some may be electromagnetic bond, some may be covalent bond, and many others. So every node and every edge have their own attributes associated with this. So those attributes with respect to nodes and edges may be of different vectors or different size. Okay, and that we call it as dimensions. So each node and each edge have their own attributes and their own properties, and they have to be taken care of because they all are resultant for the behavior of this chemical compound. Okay, so that's why the attributes should also be taken care of.
Sir, there's one question here. Can you hear me? This graph, right? G is equal to FV, right? So what exactly V here?
Okay, so V is the, wherever normally the nomenclature is, V stands for vertices and E stands for edges. There's a mapping from vertices to the mapping of, there's a mapping function from V to R or real numbers which are of the order n cross d, where n is the number of vertices and d is the attributes or the dimension of the vectors associated with that node. So suppose, for example, there are 10 different properties associated with that carbon node. Okay, so we are taking care of atomicity, molecular value, many, any, whatever you can think of, charge, number of electrons in the outer valency shell, and many more things. So this will be of order. Suppose if the order is there are 10 different factors which are coming to play. The order will be here. The D will be equals to, D will be equals to 10. D will be of the order 10. So D is a dimensional vector which contains 10 different values. First is responsible for atomic weight, second is responsible for molecular weight, third may be associated for whatever it be, dash, whatever. So I'm not, even those properties are not coming to play here. They may be different properties, and that will be equivalent to the dimension of that vector. Clear? But ultimately, crux is that if node should not be a single value. Node need not to be a single value. Node itself can have a bunch of properties associated with this. Same as the case with the edge. Edge means type of edge. Okay, whether it is a simple bond, single bond, double bond, electrovalent bond, covalent bond, ionic bond, whatever it be, and the strength between them. Okay, so what is the strength of the bond between those two atoms? Or they can be multiple properties. So even the edge and node can have their own attributes. And those attributes will be a part of vector associated with each node as well as with respect to each edges. Clear?
Sir, one
Yeah,
quick
so
question.
V is here is a domain of all vertices, right? And you're saying, right, it is to relate to a real number where n is the number of nodes and d is the dimension of your, values for a particular node. So this n will be always one, right, for a particular node, because every node can have a different attributes.
N is the number of nodes. So suppose, for example, there are 1,000 nodes. So each node has a dimension 10. So 1,000 into 10. Well, this
But
will be a
it
set
can
of
be a
real numbers.
possibility, right? Each node can have a different dimensionality. One
Each
node
node
can
can have a
have
different.
two. One node can have a two attributes. Other nodes can have a three attributes. Is it not a possibility?
In that case, it's better to make it uniform. So for example, suppose we are looking for 5 properties. Okay, so property number 1, property number 2, property number 3, property number 4, property number 5. So in that case, presence of it, or it's, suppose for example, in that case, there can be a scenario that they can have different number of attributes. I think they can, because if there are different, suppose for example, if this is not C, this is N. So N can have different properties, but different values. But I think the properties that we will be looking for should be constant. The order of whether it is absent or present, that's matter a lot. But if it is present, it may have a different value. If it is absent, its default value can be 0. But I think the order of those vectors should be same. The dimension of all those nodes should be same, I think. But I have not even thought of whether they can be of different dimensions.
Sir, we can have max of the dimensions of all the nodes, right? That is.
This I've not thought of, but this is a real-time genuine issue, because okay, fine, it can that all the atoms should have those properties, but I think the size of the vector should be uniform, I think. Not sure, I'm just guessing from my side, because we will be doing all the matrix multiplication. So if I'm doing all the matrix multiplication, then definitely it can only be done if the order of all the metrics are same. So I think the order should be same.
Can we put 0 for the attribute that doesn't exist?
That is missing, we can assign it as 0. But I think order should be there, because different
So
order.
D is the dimension for each node, right? Below it is written D is the dimension associated with each node.
Associated with each node. And I think that total dimension should be uniform across all the node. But I'm not sure exactly whether they can be. But the thing is, my intuition says that if the dimension of each node is different, then it will be difficult for us to perform the matrix multiplication, because ultimately we will be performing the matrix. We will be computing all those values based on the matrix or based on the calculus. Then I think it will be difficult for us if they are of different dimensions. So I think this dimension have to be made uniform. That may be a pre-processing activity. So if it is present, some non-zero value. If it is absent, then zero value. I hope I was able to satisfy you. I know there was a lot of questions.
So the thing is, graphs can have multiple kind of nodes. So it is not really possible to make it uniform.
In that case, well, we have to, because that is a pre-processing, because definitely as a real time, we will be dealing with the heterogeneous graph. Most of those cases, wherever you will be working on those data set, I think the assignment will be floated right today. And in that assignment, you will be working on a data set which not necessarily to be a homogeneous. Okay, it may be possible that you have to work on a heterogeneous graph as well. So heterogeneous graph means a graph which have a multiple type of nodes and multiple type of edges. So they may have a different attribute, but somehow we'll have to figure out some common way of computing between those those values between two successive nodes or two neighborhood nodes. Not necessary, but that may be a pre-processing activity that we'll have to do. Clear? Now, how to convert the graph in the form of a signals? Okay, so suppose this is a one-dimensional graph. Okay, so the graph signal shows in this figure below is, yeah, here the color of a node represent its associated value with smaller value trending towards blue and larger value trending towards the red. So they may have their own attributes, and based on their attributes, I can have a different colors of those nodes. So this is one way. So graph is smooth if the value in a connected nodes are similar to each other. So if maybe smooth, so suppose for example, the neighborhood starts from this one, and then some of them are blue moving towards blue and some of them are moving towards yellow and green. So that will be a smooth transition, or we can say smooth flow. Okay. Now, if it is not so, it will be a contradiction that one node is blue and another node is red. So dark blue node connected to a dark red. Okay, so value with the two extreme values. So that will not be smooth. So graph is smooth if the value in a connected nodes mean direct neighbors, are similar to each other. Okay, so similar to each other means suppose this is 0.4 and the other value can be 0.3. Okay, so if it is 0.4 and it is 0.8, those. So the smooth graph signal is with low frequency as value changes slowly across the graph through the edges. So that means all the neighbors of dark blue will be somewhere light blue and the greenish color. Okay, neighbors of this gray, or we can say whatever the color is of 0, will be either the yellow colors or light blue colors. Okay, so that we call that transaction will be called as a smooth. Okay, so somehow that based on those values, we are converting it into the form of some signals. Okay, so if I found something with a blue, one neighbor with a dark blue, so like this, dark blue with the dark red, this transaction is not that smooth. Okay, so this I think we'll have to check. Okay, fine. Is there something wrong in it or not? Okay, so these are the point of focus, or we can say in this case, this transaction will not be smooth.
So this means these nodes are not similar, right? They have quite different.
They may be contradictory to each other.
Yeah.
They are, that the transaction is not smooth.
So real-time example, if you have any right now, you can tell us later for this.
Now we have, but I think I have not introduced the keywords of homophily and heterophily. So suppose, okay, let me create a beat around the bush and then come up with an example. In the when I'm assigning some similarity values, we have a concept of homophily and heterophily. Okay, so similar means we are trying to find out some similarity values, and homophily and heterophily are the ways to connect between those similar values. So homophily means like-minded peoples, okay, whose similarity values are almost same. So in that case, those homophily can be considered as a smooth one, because suppose yellow, suppose if this is a gray color, okay, so gray colors will have will have a yellow colors and light blue colors in their neighborhood. Okay, so that is somehow transaction and similar type of node, a similar kind of node with some same properties. Okay, so they can be connected. They will be connected together. This heterophily structure is being used in, I think, dating sites more. Okay, so in that case, if you're trying to find out the matches, okay, probability that okay, if two users of a dating site are connected together, what is the probability that their relation will last for a day, or last for a month, or last for an year, or they will marry each other? Okay, so in that case, some properties, some nature, some attributes associated with each individual has been collected, and those contradictory nodes are connected together. Okay, so that means just a normal intuition that if someone is very talkative, he may be engaged with someone who is very silent, who is a keen listener. Okay, so in that case, those two nodes with have the extreme values can be connected together. Although a weird example, but somehow this is a scenario where nodes with two extreme values can be connected. Although that is, and that movement is not, the transaction is not smooth. Is it good? अभी मेरा चल रहा है. I hope, was it good?
Yes, I think, yeah, that is good actually. So it can be applied to the online words also, right? If we suppose we purchase any order or we purchase any product, right, and it starts showing us a similar project, right? So that can be a example also, right?
In that case, fine. Based on the properties.
Right.
So, whatever you are looking for, or whatever you have bought, what all attributes that particular product have. So or you put it in a cart. Okay, either you have put it in a cart, or you're just still surfing it on any of those e-commerce site, and similar product are used or are being recommended to you. In that case, that will be a smooth, we can say a smooth graph signals. But someone has asked for the extreme now, so there was no other example which comes into my mind except that. But for similar products like you have, okay, like you have bought, okay. So I think Google is also sending a number of mail nowadays. I think I need to check. I usually delete it. Okay, where Amazon says that something based on your own, nahin. Find a match for you. I think in trash it might be. Because I used to delete it. We found something you might like. Okay, so it is based on the nodes which have these similar values, which I have searched for something. Okay, I've not searched for this, but somehow I have searched for something else. But they recommend this type of a thing. So this can be an example for the smooth transition, a smooth graph signals near about. Yeah.
Yes, thank you.
Okay, Chalo. Thank you. We have started at 1:40. Okay, I'll have to finish this early. Okay. Um, sorry. Now the second is graph Fourier transform. Okay, so we have now again where what is the use of Fourier in this? Okay, in our mathematics also, in your calculus or somewhere, you have we have solved a Fourier transformation. Means we were given with some function, okay, and from that function based on some cosine and sine half wave sine or half wave cosine or mix of both, we were trying to convert some fx into some form of x plus e to the power something in terms of cosine and in terms of sine. Actually what we were doing here also, we are trying to do the same, but actually what is the crux and why we are doing it? So in what does a Fourier transform do? Ultimately, if you do remember, we were given some function x, okay, provided that it was differentiable and well, the limit exists and it was differentiable, so it is integrable. Okay, we were trying to break it into three parts, matlab some fx, some cos form, and some sine waves. So ultimately what we were doing, we were converting any function, any behavior. So fx may be x square. Okay, so x square is something like this. Now, if we were trying to find out a Fourier transform of x square, we were representing in some form of x plus some cosine terms, some 2 pi I and so on, cosine theta of 5 or cosine theta or something like this. We were doing it, but ultimately what we were doing, we were converting the function, whatever our differentiable function, into a some form of waveform, some form of repetitive, or we can say periodic function. Okay, so we were converting any of the function into a periodic function, so that we need not to keep track. And what is the beauty of converting into a periodic function? The beauty of periodic function was that it repeats itself after a certain interval of time. Okay, so we need not to study the behavior of the complete graph. Now here in this case, if I'm talking about fx square, I'll have to study the graph till my end point is. Okay, if my x tends to infinity also, I'll have to study the graph. But if somehow I have converted it to a periodic graph, I need not to study the whole domain of the graph. Okay, the particular wavelength or whatever the term being used, I'm missing that term. Was it a wavelength? I think. Okay, but I'll have to study the behavior in that range only. And outside, it repeats itself. So I'm not bothered about studying the complete behavior of the function. If somehow I have converted into some form of Fourier transformations, I have to study only a part, and rest of the graph will be pure repetition of this simple part. Okay, so this was the Fourier transformation, and this was the actual reason why we were doing it. So classical Fourier transform decompose a signal. Signal means any of those continuous function into a series of complex exponential part e to the power e to the power minus 2 pi it phi for any real number, where phi will be viewed as a frequency of a corresponding exponential. Somehow we were converting it into those exponentials. So these exponentials are the eigenfunctions of one-dimensional Laplace operator or a second-dimensional differential operators. Okay, so that somehow I can convert it. So traditional Fourier transformation is a cornerstone of decompose the signal into a constituent frequencies, effectively moving from a time domain to a frequency domain. This allows us, so frequency means where we have the wavelength and all those, we can say, what I think I'm missing some terms of signal processing. This was some lambda, no, what was it? I'm missing. So this altitude was something different. This was the total cyclic time or something. I'm missing those terms, but we have converted the function from a time domain to a frequency domain, which repeats itself. So this allows us to understand the underlying oscillatory component of a signal and ring and all those things. So somehow oscillating means repeating itself after a constant interval of time or a pattern. Okay, almost the same thing. So graph Fourier transformation extension that generalize this powerful concept of two signal defined on a node of a graph. Okay, so this was somehow related to, so that we have converted the graph in the form of a sequence. Apologies, I'm moving a bit faster. Okay. Then one more topic, and then we move towards the node embedding, the embedding part of the graph. Okay. Okay, fine. So 28 more slides means half an hour more. But I don't want to move on the cost of a confusion between all of you. So I'll stop here for a minute and answer any query. Amplitude and wavelengths. Yeah, fine. So that was I was talking about. Okay, so I'm stopping for a second, for a few seconds, and then would like to answer any question. Doesn't want to finish anything in a hurry on the cost of understanding.
Sir, I have a question. Can any graph be transformed into this one, the Fourier transformation?
Yes, we can. If that is, if we have, graph can be easily converted into in the form of a signals. Now, signals means repeated things. So repeated things means we'll have to, we can use that wherever we have a sequence. Suppose I think CNN convolution network is there, na, which works on a sequence. So if suppose we'll have to apply the convolution network on a graph, so this is the way by which we can convert the graph into a sequence.
So what will be the form of that after converting it into a sequence?
Was it a CNN or RNN?
RNN, sir.
RNN, sorry. That is RNN, sorry. CNN is for the metrics.
No, sir,
Okay.
for
So what
feature.
happens after it is transformed into Fourier series? I mean, what representation will it take now?
In that case, that representation will be a bit complex, but somehow we have made our model to from a graph. We can use the graph RNN model, graph recurrent neural network model. So RNN, CNN, and GNN. So there'll be few ways by which we can, there are few models in which we can use, or few scenarios in which we can convert the graph and then use it in that format. Because GNN is nothing, this is the deep learning on a graph. So deep learning has many other technique. Okay, neural network, the नहीं क्या बोल रहा हूँ, सब नहीं, कभी कभी शब्द निकल जाते हैं मुंह से. MLP, multi-layer perceptron. So if we are converted into a form of network, then MLP, multi-layer perceptron, or if it is matrix, then RNN. If it is a sequence, then if it is a matrix, then CNN. If it is a sequence, then RNN. So if we'll have to use all the flexibilities of deep learning on a graph. So if you want to use the flexibility of RNN, Okay. Now in that case, we can only use RNN for a sequence. Okay. But I am working on a graph. How can I apply the RNN on a graph? So ultimately, by using this Fourier transformation, I have converted the graph into a sequence in a series, and then I can use RNN model on that graph and get our things, whatever the prediction we want to make, we can. Okay. The second is, suppose for example in the CNN part. Okay, when image means, suppose for example, if this is an image, then every point is a pixel, and they all pixels are connected to each other in some form. But the graph has a property that sorry, the image has a property that if there's a change in a color, okay, that color will be in some pattern, in some sequence. Means a node over here will be connected only to their neighbors with a one hop or something. Okay, so it is useful for certain kind of activity. But suppose if we want to use CNN model, if we have some CNN model, some good model which gives me some good results, okay, but I want to apply that model in my graph data. I cannot do that because the graph has a property that even that one node can be connected to the last node of the graph as well. Okay, so first node and the last node of the graph can also be connected directly. Okay, or one node can be to the middle as well. So in that case, because of this property, simple CNN model cannot be used. So I'll have to somehow convert it into form of the another some other format, so that I can use that model for my graph. So these are nothing. These are because all the in your deep learning course you all have studied it, but how to make our graph, or we can say what changes do we need to made in the above my own graph, so that I can use this for the model which I know that works well in this type of a scenario. Because RNN have their own pros and cons. CNN has their own pros and cons. Okay, so if I want to use the benefit of matrix or sequence, then I can use it one or the other form. I hope I was able to set you connect between them. Okay. Next is, whenever we will be performing the classification activity or prediction activity based on some labeled data for some unlabeled data, most of the time we will be using just the similarity value. Okay, so how that similarity is being used and how the similarity is being calculated, because although you may not be directly calculating the similarity, because I think we have the library functions available. So all those library functions can directly be used, and they give us a matrix which gives us some pairwise similarity. Okay, even the edges also. But if we have some basic idea how the similarity is being calculated and what actually does that mean, then it will be easy for us to fine tune the algorithm, our model, to increase the accuracy. Okay, if suppose we are working on a black box and we have um, uh, some parameters that we have to do, we just change those parameters and find our output have increased or not. Okay, or the accuracy has increased or not. Somehow if we have find out that tuning the value of r, suppose a variable, there's a variable constant k, variable constant kya, there is a variable with the value k, or there's a variable with the fact k. If I put the value k as 0.1, my accuracy is something. If I increase the value for 0.1 to 0.5, the accuracy increases 30%. Okay, then I slightly tune it, my accuracy also increases. If I increase it, the accuracy decreases. So in that case, somehow I can relate, okay, by this pattern, I can tune k, this will be the value of k, because this value of k gives me the higher accuracy at this point. Beyond that, the accuracy decreases, but this is the parameter tuning kind of a thing. Because of this k, my accuracy was maximum. Fine, but ultimately, if I'm not knowing what is the effect of k, just चाबी घुमाने से नहीं पता लगेगा ना. मतलब if I actually know कि what had happened when my k was 0.1, what had happened to the algorithm. When I increased k to 0.2, what actually had happened, because of that, the accuracy of the model has increased. Okay, so I should know the of the algorithm also now. So that it's not the case if someone asks why it is maximum at 0.2, you say I didn't know, I performed the experiment and that gave me the maximum value, so I kept it. Okay, so that is an answer given by a technician, that's okay. But as a researcher or as an application part who is developing should not answer this question. Okay, so that's why to answer or to know what is the effect of all these things, or what is the internal connectivity, or what is the reason behind certain improvement, I can say declining of the result, we should know some numerical values and their effect. And the last thing, I think this is the last one, which we will be using, is we call it a similarity. Okay, we have slightly we have talked about structural equivalence and the regular equivalence. Okay, we'll continue in that mode only. So if I'm talking about similarity, so if we are given with and similarity between two graphs, so if we are given with two graphs, G1 and G2, okay, such that the node set remains the same, only the edge set changes. Okay, so that means G1 is one graph at a certain point of time t. Okay, then the graph changes. That can be with respect to dynamic graph. So graph changes with respect to t plus 10 times 10 hours later. Okay, so the nodes remain the same, only the structure of the graph changes. Okay, with no improvement, deletion of node, only the internal connectivity changes. Okay, so this is the meaning G1 VE1 and G2 VE2. Okay, so with the same vertices and different edge set, and I do have a node correspondence. So in that case, I want to find out a similarity score that will be a matrix, okay, of order n. Okay, so again, definitely it will be of order n cross n, because size of the graph had not changed. And this will be, suppose 1, 2, 3, 4, 1, 2, 3, 4. Okay, the number of nodes. So this will be a matrix between two nodes of a graph. So this will be for G1, this will be for G2. So in that case, any index will give me, suppose if this is free, this is 3 and this is 7, this index will give me the similarity between node 3 of G1 and node 7. Okay, so this index will give me this similarity score of each node of two different graphs, G1 and G2. And definitely it is between 0 to 1. So 0 means those two nodes are not similar to each other, means are totally different from each other. If the value is 1, that means both the nodes are exactly the same, means the similarity, they are exactly similar to each other. Okay, or it is somewhere between closed interval 0 to 1. So score 0 means totally different and 1 means identical. It can be node wise, it can be graph wise also. Okay, so if it is a matrix of nodes, it will give me the similarity of each node. It can be, if I'm talking about similarity between G1 and G2. Okay, so in that case, this will give me a single value between 0 to 1. This will give me how similar two graphs are. So if again 0 means totally different from each other, complement of each other. Is it say कि 0 means complement to each other and nothing in common? I think it should be, if I'm talking about similarity between two graphs. So 0 means totally different from each other, means G1 and G2 are complement to each other. Okay, and 1 means the both G1 and G2 are exactly the same, or else. So this is exactly the same means isomorphic graph. If it is 1, then G1 and G2 are isomorphic to each other. Okay, or else it may be somewhere between 0 to 1. Okay, we can also do it in that way also. It's a small example which I have taken from the book, which is Individual and Collective Graph Mining Principle, Algorithm and Application, in which he explained it clearly with 3 diagram. So there are 3 graphs, B10 with some connectivity, MB10 with certain lack in connectivity, and MMB10 and another subgraph of this which something missing. Okay, so B10, MB10 is missing this edge and MMB10 is missing this edge. Okay, if this rest all the graph. So in that case, if I'm bothered only about the number of edges which are missing, means added distance, okay, difference in those two graphs, just number of edges which are missing, then in that case, similarity score of MB10 and similarity score of MMB10 should exactly be the same because they both are missing by 1 edge. But ideally, the similarity, the missing penalty of missing this edge should not be much as comparison to missing the bridge. So just by removing this edge, both the graph become disconnected. So that means the penalty on missing this edge should be higher as comparison to this. Although by this, if this graph is missing this, the connectivity may be weakened. Okay, slightly weaker connectivity, but missing this edge has all the more disconnected the graph. So similarity scores should not be only focused on the number of missing edges. They should also take care of type of missing edges also, which hampers a lot. Okay. So, okay, fine. Click was. So MB10 and MMB10 have the same similarity score, but clearly the missing an edge with a click does not play an important role in the graph connectivity as missing a bridge. So click versus bridge means a click means almost a complete graph, a densely connected graph. So missing an edge has a minimal impact on overall connectivity, whereas missing a bridge has made the graph disconnected. So critical bridge connecting two clusters, its absence would disconnect the graph or increase the path length dramatically. Okay, that can suddenly increase the path length. This may be the shortest path between them. This may be a we can say what was the property that we have learned? Edge betweenness. Okay, so the edge betweenness of this edge may be very high. So if we remove it, the graph might still be connected, but path length increases. So there's two-step process for the graph similarity. The first is the conceptual step to complete the pairwise node affinities in the first graph. Okay, so pairwise affinity means similarity scores. So pairwise node affinity in the first graph. Okay, so if I'm given with the G1 and G2, so first one will be the pairwise, means how similar those nodes are of G1. Okay, to compute the pairwise node affinities in the first graph, and then compare them with the one in the second graph. Okay, so first, how similar those nodes are among the same graph, and then second is we'll have to compare them with respect to the other nodes every node of the second graph as well. Okay, so for Brittle compactness, we store them in an order of n cross n. The matrix will be S. So any entry Sij is an entry of matrix indicating that the influence node I has on node J. So the second conceptual step is to measure the difference in the corresponding node affinity scores of the two graphs and report the result as their similarity scores of the nodes between two graphs. Okay, nodes, two nodes of a different graph. A bit of mathematics. There are some properties. So if two graph G1 and G2 with the two graph, and I do have a similarity matrix between G1 and G2, which have all the values from 0 to 1, they should follow some property. That has to be identity, means if I compare the similarity of the graph with itself, the similarity should be equals to 1. Means the algorithm should be capable enough of the algorithm should be capable enough of identifying the isomorphic cases. Fine. Similar type, same graph but with different orientations. So that should be capable enough of. Second is symmetric property, means if either be the order of the graph, the similarity score has to be the same. If I'm comparing G1 with G2 or G2 with G1, the similarity score has to be same. Okay. One is the identity and another is the symmetry. The third is the zero property, which means that similarity of G1 to G2 tends to 0 for n tends to infinity. Okay, where the n is, so G1 is the complete graph of k nodes, G2 is the empty graph. So the H sets are completely where complete graph and the empty graph, means if my two graphs are complementary to each other, the similarity scores between them should be towards 0. Okay, so that means if the similarity is reducing, then our algorithm should be able to capture that. And when both the graphs become complement to each other, the similarity score should move towards 0. Okay, so that means the change in our algorithm should be capable enough of changing the similarity scores. Okay, the similarity increasing or decreasing. There are a few more intuitive. There are some more properties. Intuitive means whatever the algorithm is should be weight awareness. Okay, so in a weighted graph, bigger the weight of the removed edge, the greater the impact on the similarity score should be. Okay, so our similarity computation should be weight aware, means we should be capable enough of dealing with the weighted graph. But if the weight of the removed edge is higher, then the impact on the similarity score should be more. Second is the focus awareness, means any random changes in a graph are less important than targeted changes in the same extent. Okay, so if I'm making some changes, making some changes in order to achieve something else. Okay, so they should be given more importance as comparison to make any some random changes. Okay, so remove some edges randomly, and then we'll try to look, okay, how close our algorithm is based on the desired output. Okay, so those activities should be given less importance as comparison to the systematic approach. The other one is, whatever our similarity scores is, it should be scalable. Means the huge size of the generated graph as well as their abundance requires a similarity measure that is computed fast and handles graph with the billions of nodes. So whatever our algorithm is, if it is working a smaller size, it should also work in the same way for a bigger graph as well. So whatever our approach is should be scalable. Okay, so there are a few proposed technique to find out the similarity scores. I think edit distance and graph isomorphism we have already discussed. I've already explained you in the I think first few sessions. Feature extraction and then iterative method. We'll look at it. This I think I have already explained you. Two graphs are similar if they are isomorphic. Okay, so one is the isomorphic to subgraph of other, or they have an isomorphic subgraph. The drawback is the exact version of the algorithm are exponential and thus not applicable to a large graph that are of interest today. Okay, so to deal with the isomorphism, we have a comparatively easy technique. We call it as WL algorithm. Okay, which is being used in a large graph to identify whether two graphs are isomorphic or not. Okay, so we'll discuss this WL algorithm in detail, which take care of this graph isomorphic problem. Okay, the distance is the same. If okay, just for sake of completeness, let me read it. So graph edit distance is a generalization of a graph isomorphism problem where the target is to transform one graph into another by doing a number of operations. What kind of those operations can be? Either the addition, deletion, substitution of node or edges, or reversion of those edges. Okay, so all those properties are allowed, all those operations are allowed, and number of times we are doing it will be equivalent to the edit distance of that node. So this method associates each operation with a cost, and it attempt to identify the sequence of operation that minimize the cost of matching two graphs. So this can also be used for graph matching. The second technique was the feature extractions. Okay, so this was suggested by two of those researchers. How much time do I have? Do I have sufficient time? 40 minutes or yeah. Okay, so the key idea behind all apologies for moving a bit faster, but I'm already late. So the key idea behind this method is is that similar graph probably shares common properties such as degree distribution, diameters, and eigenvalues. Okay, so if those eigenvalues, diameters, degree distributions are same, then chances are there that those two graphs may be similar to each other. Okay, but not necessary. So after extracting this measure is applied, suggested by this, in order to assess the similarity between the aggregated statistics or and equivalently the similarity between two graphs. Okay, so if all the factors are same, then I think the chances of being similar is more. So these methods are powerful and scale well as they map the graph to a several statistics that are that are much smaller in size than the graph. The diameters and all those are has a very small diameter. These are the single values. However, depending on this even the degree distribution, the degree contribution, and so on. So depending upon the statistic that are chosen, it is possible to get the result that are not intuitive. So it is possible to get a high similarity between two graphs that have been very different node set, which is not always desirable. Okay, it may be possible that by using this feature extraction, we may end up a scenario where two graphs sounds to be similar to each other, but we found that they have a different node size. Then in that case, our feature extraction method will fail. Then the third one is the iterative method. They works on the idea that two nodes are similar if their neighborhood are also similar. What is it? If you do remember, we have just covered it in the beginning of this session, regular equivalence. So in each iteration, a node exchange similarity scores and their process ends when convergence is achieved. So that method is called as similarity flooding method, suggested by him. Okay. So this algorithm solves the matching problem. It attempts to find the correspondence between nodes of a two given graph. Okay, I'm given with two graphs. We just find out how well one node of a graph is matching toward the another node of the graph. So one algorithm was similarity flooding. So the way of algorithm is evaluated is human check whether the matching are correct and accuracy of the algorithm. The number of adaptations that have to be done in the solution in order to get the right one. The another method was the simring. Okay, this has been widely used. We call it as simring. It was suggested in the year 2002. Okay. So what they come is they come up with a structured way of finding out the similarity between two nodes, nodes of two graphs. So it measures the self similarity of a graph. That is, it assesses the similarity between all pairs of node in one graph. It is based on the notion of similar nodes have the similar neighborhood. So how does it do? It computes iteratively all pair similarity scores by propagating the similarity. A square matrix means distance of hop 2, where AGHS is matrix of graph 2, and process end when the convergence is achieved. Now, how does it do? So there were few methods suggested by various researchers. Initially, it was suggested by Klingberg in the year 1999, and then it was updated by Blondel in the year 2004. Okay, and the method that the Blondel. So this Blondel is, I think, I think you have we have come across this paper earlier also, but not in that sense for finding out similarity. I think in terms of connectivity also at that time. Okay, so he come up with an update rule, and as this is an iterative method means we will have a matrix. Okay, so based and like a Markov chain. So based on the matrix of order k, somehow we compute the matrix, and then from the this matrix we found out the similarity scores of each node at of iterative k plus 1. Okay, so update rule is this, and here the power, so k and k plus 1 dash 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 are the iteration. Okay, not the power. They are not power of that matrix. A square of that's not the case. Okay, so that means using the values of this matrix. Okay, so this will be of order n cross n, some I. So suppose p is here and q is here. Okay, for some PQs, combination of the similarity scores of the kth iteration. From the kth iteration, we will be updating the similarity scores for k plus 1th. Okay, so this is the meaning behind this power. So this is not the power. This is the I'm updating the I'm trying to find out the similarity scores of the next iteration from the scores of the previous iteration. Okay, and the summation time, I would just like to. So suppose, for example, I'm trying to find out the similarity scores of from a matrix X, okay, for a particular node I and J. Suppose, for example, I is 3 and J is 7. Okay, so that means this is of graph A and this is of graph B. So I'm having two graphs, A and B, and I'm iteratively updating the values of the similarity scores. Okay, now, okay, I'll answer that question of initial value later on, but let me explain you in the terms of mid. Okay, so I'm trying to find out the similarity scores of node 3 of GA and node 7 of GB. So GA has an H set EA and graph GB has an H set EB. Okay, fine. Now here PQ is varying. Okay, so XPQ. Okay, so this is the similarity score iterative wise similarity scores of the nodes of two graph. So GA are this and GBs are this. Clear? There is some PQ. For example, suppose this is P, this is P, and this is some Q. And I'm trying to update this value. Okay, 37. So, sorry, I should not write in terms of PQ. Sorry, my bad. 7 something. Okay. Now, now, based on, as this is an iterative method taking care of structural properties, so that means you'll have to be with me. So I will be adding the similarity scores. I will be updating. I will be getting updated similarity scores based on the previous similarity scores and based on the neighborhood. Okay, so that means I'm summing all those values, summation of all those PQs, which all values will be there in PQs. So suppose, for example, from P so all those PIs from EA. Okay, so PI means all those edges. Okay, whose end product is I and end product is 3 from EA. So that means, what does it mean? It is the I'm updating incoming neighbors of 3 of GA and 7 of GB. It means the same. All those P3, 1, 3, 2, 3, 3, 3, 4, 3, 5, 3, whoever it be, if it is 0, it will not participate. On only the non-zero value will be accumulated. Okay. if those are not directly connected, those values will not be participating in. So all those PIs, so incoming neighbors of 3 in EA, and all those QJs, so 1, 1, 7, 2, 7, 3, 7, 4, 7, 5, 7, that belongs to H set of B, means all the incoming neighbors of 7, node 7 of EB, of GB, incoming neighbors of node 7 in the graph B, and incoming neighbors of node 3 in graph A. Their similarity scores is being added. So that means this XPQ at the kth iteration, these are the similarity scores incoming neighbors of 3 and 7 respectively. So their incoming, their scores are being added. This is the meaning behind this summation. Okay, is this clear? I'll take a pause for a minute, and then please let me know if this expression is clear or not. Although it is just a mathematical expression, but this is the physical interpretation. So I am updating the similarity scores of a particular node at the kth iteration based on their own incoming neighbors. Clear? I need a yes from your side. Is it so?
Node structure will remain same, right? Yeah.
Node structure
Will remain same. I mean, every node will have the same position.
No, I'm not changing the node structure. Na? I'm just update. This xi is updated every time.
So this is the same thing, right, which we have seen in the Excel sheet, right, where we were calculating the differences between the nodes
Where?
by taking the neighbors of node, if I'm not wrong.
That is a centrality calculation.
Sorry.
That is a centrality calculation in the page rank calculation.
Centrality was something else. Centrality was a node with respect to each prop. Centrality was based on same graph. Okay, this is the similarity of nodes being computed based on the incoming neighbors and outgoing neighbors of the nodes of both the graph. So this is the similarity of two nodes of a two different graphs.
Okay, yeah, got it. Thank you.
This is the similarity of similarity scores of two different nodes of two different graphs. How similar those two graphs, and their similarity, the node of this similarity is calculated based on their incoming neighbors and their outgoing neighbors. Okay, so this is the incoming neighbor. Similarly, if this is 3, 7, so 3, 1, 3, 2, 3, 3 means outgoing neighbors. So that means I am taking care of incoming neighbors plus outgoing neighbors of 3 of GA and 7 of GB. And what I'm adding? What is the value which I'm adding? I'm adding the similarity value of their similarity value of the previous iteration. So what does it mean? After every iteration, the similarity scores is updated. Like a page rank, if you do remember. Okay, so after every iteration, the similarity score of pair of nodes is updated based on what is the criteria for updating the similarity score? Based on, please help me to write this word. Based on what? Similarity scores, their similarity scores, SCORES, in previous iteration. Okay, so obviously it has been updated. So the moment it reaches to a convergence, I will terminate. Okay, and every time I'll have to normalize it. So I will normalize it by mod of x square. Clear? So this was the example which they have solved. So they come up with this is GA and this GB. They perform this iteration after certain number of times, after certain number of iteration. They terminate the algorithm because their similarity scores might have converged. Okay, and when it was converged, so this is the S matrix, which gives the similarity score of GA with similarity scores of GB. So this is node number 1, 2, 3, 4 of GA, and this is node number 1, 2, 3, 4, 5, 6 of GB. So this point means 4 and 3. So this is the similarity scores between fourth node of GB, means this one, and third node of GA, means this one. So the similarity between this and this is what? 0.2870. Based on what? Based on the neighborhood of node 3 and neighborhood of node 4 itself. Clear? So this is the final output value after the iterations have converged. Now this will be very well used in most of my classification problems, because I will be assigning a similar label to the similar nodes which are still unlabeled. Now, how do I identify the similarity? Based on this. Clear? A bit of mathematics, but I think is it clear now? Please confirm so that I can move forward. I cannot leave you behind guessing, and please confirm. Is it good?
Yes, sir. Yes.
Okay. Chalo. Okay, so not only this, he also performed experiment for graph on the corresponding self similarity matrix. So means for the self similarity also. Okay, so the similarity of nodes within themselves. So this is the similarity scores of this graph for GA. This is GB. This is GC. Means similarity scores of the similarity scores. Okay, so in that case, where this can be used. So for example, if this is the similarity scores for node 3 and 4. So that means node 3 and node 4 are exactly similar to each other, as well as node number 1. So in that case, they can be swapped. They can be replaced by each other or something like this. Okay. Now, model, this was the formula for Blondel. in the year 2004. Now, in the year 2008, there were one more researcher who come up with an updated formula for similarity. Okay, and the name was Zeger and Verghese. So what does they come? They come up because still this method of Blondel was giving me the similarity of nodes among themselves. Okay, nodes across the two graphs and nodes across the same graph. So he was primarily focusing on the similarity of the nodes based on their connectivity. They move one step ahead and they coupled the similarity scores of the nodes as well as the edges. Okay, so based on the similarity of nodes, they computed the similarity of the edges, and based on the similarity of the edges, they updated the similarity scores of node. Okay, that also in then iterative manner. Okay, so they start with the initial values, and then based on node, they updated the edge similarity, and then based on the updated edge similarity, they update the node similarity of the next iteration. Then based on the node similarity of the previous iteration, of the next iteration, and so on. Okay, so it is a two-step process. Okay, so in that case, again, this power, this subscript, superscript is not the power. This superscript is the iteration. Okay, based on the values of previous iteration, they update the values of the next iteration. Now, what is the criteria that they use? That the update rule for the edge similarity was based on the matrix similarity, based on the node similarity. Okay, so using the previous iterative node similarity, they update the similarity of edges. Now, how come? So suppose again, if they want to, so this is an edge. Okay, so YUV. So suppose this again, let us talk about 3,7 only to make it simple. Okay, so node 3, no, 7 is not 3, 4, 5. Can I make it 3, 4? Okay, because 7 is not there in this example. So U is 4 and U is 3 and V is 4. Okay, so that means U belongs to the edge set of A, means U belongs to the graph A, and V belongs to the graph B, means 3 is from the graph GA and 4 is from the graph GB. Clear? This is the meaning. Now, and this is the iteration. So based on the previous iteration, the next value is updated. Okay, so this will be a rectangular matrix. Now, node 3. Sorry, very guilty. These U's and V's are the edges. Okay, let us take 3, 7 only. So this 3 is the edge of GA and 7 is the edge of GB. Okay, as this is a directed graph, so what is the source of 3? Source of 3 is 4. 1, 2, 3, 4. Source of 3 is 4. And what is the target of 4? Target of 3 means the another endpoint of this edge. Endpoint of this edge is 3. Okay. What's the source of 7? Source of 7 is 2. Source of edge number 7 is 2. And what is the destination of edge 7? Destination of edge 7 is 1, 2, 3, 4, 5. If it is 5, let me check. Is it 5? No. 6. Let me write it correctly to avoid any confusion. So target of 7 is what? 6. Okay. Now it is just mere the index values. So SU is, so this is U, this is V. So 4, 2. Okay. So 4 from GA and 2 second location from GB. So this will be a matrix, square matrix. Okay. Or it can be a rectangular matrix as well. Fine, take it, whatever it be. But this is the index from the similarity matrix, a node similarity. And target means target of U is 3 and 6. So 4, 2 plus whatever the value was at 4, 2 plus whatever the value was at 3, 6 was added into the edge similarity value of 3, 4. Edge 3, 4. Okay. So based on the node similarity, the edge similarity value is updated, and based on the edge similarity matrix, the node similarity matrix is updated. So based on this, I have updated this. Based on this, I'm updating it this at every iteration. Okay. So TU, TV, SU, SB. So based on that, this value was updated. So this was a comparatively better approach in which we ends up getting two different matrices. This is the node similarity, and this is the edge similarity matrix. Sorry. Okay. So this is for G. This is A and this is B. Okay. So GA and GB. And this is for GA. And these are for the matrix GB. So this gives me the similarity. So suppose, for example, if this is the value, what does this mean? This is the similarity scores of node 4 from GV and node 2 from GA, as well as suppose this is the similarity scores of the edge D from GV and edge B from GA. This AB is not based on this. Sorry. Meri galti. This AB is based on this graph. This is the A graph and this is the B graph. Fine.
So, sir, I have a query. So it is taking into consideration the edges one. So the only benefit is only in special type of graphs that I see, that especially where you have maybe like a, like we divided relation like directed graphs, I would say. Do we have any other like benefit for undirected graphs for this new method with the edges one?
In that case, matlab, it is very well suited for, matlab, it is for directed graph. Okay, so if I want to do it for undirected graph, I can do it. Matlab, handling the undirected graph is comparatively easy in this kind of a similarity one.
Of course, yeah. So like I said, like
In that
we
case,
last
it will
time
be
also
symmetrical.
yeah. So last time we discussed that only in divisible case relationship, there we were, I can see still this edge one, but giving an upper hand always, because the relationship are not the same when you with or in case of divide or maybe any other relationship that we consider. And in those cases only this will be better than the only node comparison one. I think this is my inference so far. Is there any other case, or it can be for all the cases it will give a better results? That was just the query that I was thinking of.
I'm not able to understand the reason you're talking about division. Where are we performing the division operation?
No. So only in cases where the relationship between these nodes, like that means the edges are the relationship changes from one direction to other direction. Those cases, I feel this edge method is will perform better, and on all other cases the both will give the same comparison similarity because only the nodes are compared. So that is what my inference is so far from both the methods.
In that case, in this case, this method, suppose suggested by the Zagar and Verghese, take care of the node connectivity as well as the
Edge, yeah.
edges as well. Okay, so that means this take cares, or we can say this include more information about the graph connectivity. So this similarity scores is more we can say graph connectivity oriented as comparison to the Blondel method. So Blondel only updated the similarity scores based on their neighborhood, neighboring node. But Zagar and Verghese calculate the similarity scores based on the connectivity as well, based on the edges as well. So because this was published in 2004, the Blondel was published in 2004, and the Zagar and Verghese published this work in 2008. So that means this method is updated one, and this was they have come up with an updated, or we can say
Comparison.
not advanced. Advanced to nahi kahunga. The updated computational method.
Got it. Yeah. Thanks.
Okay. They come up in the year 2011. Okay, for the subgraph mining. So they describe a new approach, the method of neighboring matching. Okay, so in the first one we were talking about the neighborhood. Then in the second method, we talk about type of connectivity as well, about the number of edges. Then they the second or updated one also take care of the neighbor matching. So for measuring similarity of this code on the graph, they defined a measure of similarity for the whole graph based on the similarity of their nodes. So their formula is still a bit complex, but they include much details about the graph connectivity. So two nodes I from A, VA, and J from VG means one node from from a graph A and one node from a graph B are considered to be similar if neighboring node of I can match to the similar neighborhood of J. Hence, the name neighbor matching means somehow I am updating or I'm taking care of regular equivalence as well. Okay, so they are differentiated between the in similarity and out similarity. Similar incoming neighbors and based on the outgoing neighbors, and give them equal weights. So in order to calculate the insimilarity, the matching of in neighbors with a maximum sum of similarity has been constructed, and Similarly, for the outgoing similarity, the maximum sum of the similarity for outgoing neighbors were calculated. Now the update rule is a bit complex. Okay, please do not be diverted away because you need not to, I'm not asking you to implement this, but just have a brief idea how this has been and I've updated it. So what does the, okay, take care. I'll start from the top. So he computed the incoming neighbors. So this again, this superscript is not the power, it is the iteration. Okay, so he computed the incoming similarity and outgoing similarity somehow. I will explain it, but somehow he have calculated the in similarity and out similarity and then take an average of both this one plus this plus divided by 2 to show to have the similarity of overall. Okay, so somehow he have calculated the in similarity, somehow he have calculated the out similarity, then take an average of both to give me the the graph similarity of the node xij. Okay, so that's why it is k plus 1 k plus 1, and so take off average of the same iteration. So this again is the k plus 1. Okay, so k plus 1 k plus 1 k plus 1. Okay, fine. Now let us come back to this, how he computed the in coming similar in neighbor similarity and out neighbor similarity. Now, so in neighbor similarity, he computed, he normalized by something 1 minus 1 by some value, some factor. Okay, so this is nothing, this is the normalizing factor norm. Okay, so m in some normalizing factor that is run that depends upon the current connectivity of the graph. Okay, so some normalizing factor. Clear? So sk in 1 by something, sk out 1 by something. Okay, so what is m in and what is m out? M in is the maximum of the in degree on which we are working, xij. Okay, whoever has the maximum in degree, I normalize it by them. Okay, whoever has, if I'm working on node number 3 and node number 4, so whoever has the maximum in degree, I will normalize that value by, I will normalize the similarity score by maximum of that degree. Okay, so that's again a normalizing factor. I think that's clear. Max of the value, max of any of that in degree, I will use that maximum degree as a normalizing factor. So m in is max of whoever has the maximum degree. Same is the case. M out means whoever has the maximum out degree, I will normalize the degree by that factor of that node. Clear? So this is also done. Now come up to the summation rule. Okay, so if I'm finding out the incoming neighbors, so for all those L from 1 to n in, what is n in? Minimum of the in degree. Whoever has the minimum degree will be my common neighbors. Okay, so whoever has the minimum one, I will not the common neighbor. Whoever has the minimum in degree means a lower threshold. Okay, I will compute it till that number only. Okay, so L equals to L to n in means whoever has the minimum in degree, I will perform that much of iteration only. Okay, rest I will not compute. Same is the case. N out, for calculating the out degree, L equals to 1 to n out, whoever has the maximum out degree. Okay, so this is the number of iterations, or we can say neighbors I will be summing up. Okay, what will be the size of the neighborhood in which I will be computing those values. So min of their in degree and their min of their out degree respectively for sk out. Okay, this is k plus 1 and this is k. So from the previous iteration, I am computing the next iteration. Clear? Okay, let us come back to this. Okay. So for L equals to 1 to Nn. So suppose if this is ij, I is 3, 4. Okay. So xk for all those L from 1 to N, minimum of all those who are connected to those 3, 4 in F and G. Where what is F and GI, FFIN or GIN? They are the enumeration functions for matching the in neighbors of node I with the weight function, this one, which is an analogously their outgoing function as well. Okay, so somehow how the sum has been weighted up. Okay, as this is a directed weighted graph. So how I will add all those incoming neighbors and all those weights of those incoming edges and weight of all those outgoing edges. I will be adding all the values. Okay, so based on those, I find out the SK in and out, and then take an average. It will be the similarity score of that node of that iteration. Okay. Fine. This is merely a case where it is. So we define 0 by 0. Now in that case, there may be some special cases in which we have a 0 by 0 case. So 0 by 0, in that case, we will be replacing unit vector. So this convention ensure that the similarity of score with no in or no out neighbor is recognized. Means sources and sink has to be taken care of. Because for a directed graph, these are the problem areas, sources and sink. Because sources have degree and sink have 0 out degree. So if there's no difference in the number of in and out neighbors, then the difference is penalized when calculating the similar TK greater than the number of fine. This can be the normalizing factor, and that's all. If I do have a time, oh sorry. Okay. What I have done is 6A is done. Laplace is done. Okay, node embedding and knowledge graph is left. Okay, no issue. I will take this in the next session. Okay, next is the knowledge graph, and then immediately we will move towards the node embedding. Okay, sorry, we will move towards the node embedding and then GNN. Okay, sorry for taking 10 minutes extra. Oh, so much of. Suppose we compare Bangalore. Start with the station having equal similarity if Delhi Rajiv Chowk connected to many stations in Bangalore Majestic also connects to many stations, their similarity increases. Correct. The iteratively update based on the neighbors. If Rajiv Chowk connect to the station that are similar to Majestic neighbors, similarity grows. Fine. Normalize after every iteration. Okay. We'll have to normalize to reduce the effect of superfit individuals. After convergence, we'll know which station are important junction and how. Okay. The only thing we have to make sure that the network comparison, like we move from Rajiv Chowk to Patel Chowk neighbors and Majestic to Kampagoda neighbors, we should have old similarity scores from the previous iterations. Yes. So Vikram, have done that good analysis. Okay. So we'll continue in the next class. So Upendra, yes. So I'll stop the recording. So thank you, Vikram, for this nice analysis. This again, some sort of network analysis.